So
Okay.
welcome to Veronica. So welcome to today's lesson on semiconductor physics, where we are going to look at special purpose semiconductor diodes. I hope you can see my screen.
Yeah, I can see it.
Good. So among the semiconductor devices which we're going to look at, one of them we're going to look at is, there are several types. So just a moment. We have, we're going to look at the first one, which is the Zener diode. So a Zener diode is a special type of diode that can handle breakdown without failing completely. It's a diode which operates in the Zener voltage region, and it operates in the reverse bias mode. So when you actually check, this is the circuit diagram of the Zener diode. In the forward bias, it usually operates normally, but in the reverse bias, if you can be able to check here, remember when you look at the current voltage characteristics of a diode, we have the forward voltage region, whereby as the external voltage, when it's in the forward bias mode, the external voltage is increased at some point, usually what you call the forward voltage of about between 0.3 to 0.7, then it can be able to conduct current in forward bias. This is basically due to the recombination where electrons, they cross over and they combine with the holes from the P region, and therefore now the potential barrier is overcome. Now the Zener diode, on the other hand, it operates in this reverse bias mode, what you're calling the Zener voltage. At the Zener voltage, this is the voltage at which now, usually in the reverse bias, there's what you call now the minority charge carriers which flow. And so as the minority charge carriers flow, it reaches a point where the gap between the P and the N continues to extend until we reach what you call the breakdown region. So the Zener diode is made to operate at this particular voltage, where it is designed to be able to allow current to be able to flow at such a particular voltage. So when connected in reverse bias mode, you can be able to see here, a small leakage current may flow. But as the reverse voltage increases to a particular predetermined breakdown voltage, what you call the Zener voltage, then current starts flowing through the diode. Remember, it is already in reverse bias mode. So the current increases to a maximum, which is determined by what you're calling the series resistor, after which it stabilizes and it remains constant over a wide range of applied voltage. So the reverse voltage can be quite large, but the Zener voltage remains very stable for a large reverse voltage, and it can be able to allow current, a large current to be able to flow. So uses of the Zener diode, these are some of its applications, and you're going to look at some of them, especially the voltage regulator, and also it can be used as a meter protection device against the damage from accidental applications. So as a voltage regulator here, you can be able to see our Zener diode over here. So the input voltage, when the input voltage equals the Zener voltage of the diode, then the series resistor limits the current through the diode and drops the excess voltage when the diode is conducting. So when the voltage, the input voltage equals the Zener voltage, then a lot of current is going to flow through it. And as current flows through it, then a potential difference is going to be created across the resistor here. So the output voltage which is going to give, it will be equivalent to the input voltage here. And as more and more current flows now, that potential difference can be recorded across the resistor. So so this one protects the load here, such that if there is if there is the voltage, it goes beyond the Zener voltage, then that excess current can be able to flow through the resistor here. Then another application is the meter protection. So you know that sometimes the meter, It's actually the one which can be able to indicate the consumption, the power consumption, all that. And also it can just be some devices which have the meter, the ammeter, the voltmeter, which can be able to measure different maybe current characteristics. So the meter movement is protected from any damage as most of the current passes through the Zener diode. So remember we said that the Zener diode can be able to allow a large current to be able to flow it without damaging it, especially when it's operating in the Zener voltage. So in case of any accidental overload, so let's say that maybe there is more current which is flowing from maybe the positive terminal or the negative terminal, you can be able to see that that current will be passed through the Zener the Zener diode, which is in reverse bias, and it can be able to withstand that. So that one, that excess current flows through this, and it now prevents current from flowing through the meter. It will be protected. So any extra current will be conducted through the meter. Now, the diagram below here, it occurs when the polarity of the surge voltage keeps on changing. Like when, for example, you have an alternating current is passing. So here you can be able to see we have two Zener diodes here, such that when the polarity changes, maybe this one goes to negative. That means if it goes to negative, it means this one will be reverse biased. If this one goes to positive, then this one will be reverse biased. So in whichever case, please somebody mute your mics. Huh?
Okay.
Mute your mic so that we can. Yes.
I'm using it now.
Eh?
I'm using it now.
Yeah, I've muted you so you can be able to minimize the echo effect. So the diodes can be joined in this way, such that if the polarity keeps on changing, especially for the case of alternating voltage, then or alternating current or alternating voltage, then it can be able to be in reverse biased, whether it is flowing from this positive direction or even when the polarity changes to negative. So basically, here it is being used as a meter protection, where if there is excess current flowing, it can be passed through the diode, therefore protecting our meter on this end here. The other type of diodes which you want to look at, they will call them the Schottky diodes. So the Schottky diodes, they are constructed by joining a doped semiconductor, usually the N-type, with a metal, usually gold, silver, or platinum, rather than the usual PN junction. It is also referred to as a hot carrier diode. So this is the circuit symbol of the Schottky diode. You can be able to see it over here. This is the circuit symbol. The anode is on this side and the cathode is on this side. You want to understand more about it. If you can be able to see this diagram here, we have instead of the PN junction, we have a metal N junction. Then you can be able to see our junction, our barrier, our potential barrier here, it is very, very small, because you know that metals, they have very many free electrons which can be able to flow. So the anode is made of the metal and the cathode is made of the N-type, which is the silicon. So basically here it is a unidirectional device which is conducting current only in one direction, from the metal to the semiconductor. So when it is forward biased, when it is in forward biased mode, the metal is connected to the positive terminal and the N-type is connected to the negative terminal, so that now electrons can be able to flow in this particular direction here, from the metal to the N-type semiconductor. Now, our junction here, it's our potential barrier is very, very narrow. That means just by giving it a very small forward voltage, it can be able to go into a conducting mode. Then if you the current voltage characteristics of the Schottky diode, you can be able to see here as opposed to our usual PN junction, which has, you can be able to see its new voltage. It is forward voltage, it's slightly higher than what you call the Schottky diode. You can be able to see it is very, very small. Yeah, that means by the application of a small forward voltage, it can be able to start conducting. Equivalently, even in the reverse bias, you can be able to see the leakage current is relatively higher as compared to our normal PN junction. What are the characteristics of the Schottky diodes? They are usually characterized by what you call fast switching. So they can be able to switch very fast because just a very small voltage, look at that, typically 0.25 to 0.4 volts, as opposed maybe to a normal PN junction, which requires somewhere between 0.3 to 0.7 voltage for them to be in forward bias mode. And then another characteristics that they can be operated at a much higher frequency than the usual PN junction. These are some of its applications. They're used in high-speed computer circuits where the fast switching time usually equates to a high-speed capability. They can be used in the rectification. Remember the rectification where you can changing the AC to DC. Because of the very fast switching, then they can be able to be rectify faster, and especially at higher frequencies than the normal diodes. And they're also used in what you call clipping and clamping circuits, and they're used in mixing and detecting circuits, and also in low power supply circuits. So they have a number of applications, and you can be able to just remind ourselves the usual diodes, the way they are able to do rectification. So the Schottky diodes can also replace the normal diodes here to be able to do rectification, converting from AC to our DC. And then we're also going to look at the light emitting diodes. So a light emitting diode is a PN junction diode which emits light when in a forward bias mode. The emitted light may be visible or invisible. So invisible, usually you know that like the invisible light could be what you call the UV. The UV, the ultraviolet light can be emitted. So they can be able to emit the visible or the invisible. This usually done through what you call recombination of electrons and holes in the active region, which yields what you call photons or light. This process is referred to as electroluminescence. So to be able to give off photons, the potential barrier through which the electrons fall must be higher than the diode. So definitely the applied voltage must be greater than the what you call that potential barrier of the diode. And the forward diode drop can range from a few volts for some colored LED. So you can be able to see when it is in forward biased mode, it emits light, or what you're calling the photons. And you can be able to see that, for example, this is emitting the red light. So diode can be made from a combination of elements, especially the group 3 and the group 5 elements. Gallium arsenide, for instance, or gallium phosphide, can be able to see there. Or it can be a tertiary, like gallium arsenide phosphide. So these ones have been known to be able to produce bright red light. So this specific combination of gallium arsenides, what you're calling the gas, gallium arsenide or gallium phosphide, they usually be able to give the red light. And by altering the combinations of the group 3, group 5 elements, different types of colors can also be produced. So just the physics behind that, you can be able to see inside here, we have the p-type and the n-type. You can be able to see the hole, the electrons, and the holes. This process of electrons and crossing over to meet with the holes is what you call recombinations, the electron-hole pairs. As they recombine, then that recombination can be able to give out some photons, or they can be able to give out some light. And this is just an illustration of that. Remember the electrons are in the conduction band and the holes are in the valency band. So so there's kind of a decrease in energy when electrons move to the side of the holes. That movement for them to be able to recombine can be able to produce what you call photons. So you can be able to see as the electrons are moving down from the conduction band to the valency band, they are able to emit some photons. And I want to be able to say this, that this one usually happens in what we call direct band gaps. Remember, we had discussed on about direct and indirect band gaps. So this one usually happens for a direct band gap, whereby the electrons are just able to move direct and able to do recombination. So that recombination is radiative. You can be able to radiate light in the form of photons. So this is also just as an illustration. You can be able to see our LED here be able to produce photons. And this one has happened basically due to the recombination, whereby the electrons are moving in that direction as the holes are moving in that direction. And this kind of recombination is what is giving us the light. So depending on the group 3 and the group 5 elements, they can be able to give different types of light. And we have said for red light, usually it is gallium arsenide, a kind of combination, or gallium phosphide. Just to understand this better, because it's an area which maybe some of you are going to explore in your research, you can be able to see now the different layers, how they are structured. We have what you call a substrate. So a substrate is basically the material now upon which the layers can be grown for them to be able to work as our LED. So we have our substrate here. Then the N-type is placed here just beneath the substrate. Then we have our active region. So the active region is where recombination is going to take place. Then you have the P-type. So what happens is that when now the electron, when voltage is applied, then recombination is going to take place. This is the active region. This is the region now where light is going to be emitted as electrons combine with the holes. They have a number of applications. One of them, they are used for indicating the on-off condition. They are used in the 7-segment LEDs, what we call usually the 7-segment display, made just right from the display of the digital displays which you have, right from maybe the watches, like from the, so any output, any digital output usually uses what you call a 7-segment display or 16-segment, and what you call the dot matrix displays. They're used in optical switching, they're used in burglar alarm systems, and also for image sensing circuits in picture motion. So this is just a circuit diagram. You can be able to see the applied voltage here. Then of course it has a resistor which can be able to protect it, especially in case maybe the voltage is too much. And it is in forward bias. So basically, as current flows through, or as this voltage is applied and it overcomes the potential barrier, then it can be able to emit your light. And the resistance across the LED, or the resistance here can be the voltage across the source minus the voltage across the LED divided by the current which is now going to flow through the LED. So that's how you can be able to calculate the resistance. Let me also mention very quickly about the photodiodes. Photodiodes, as the name suggests, these are diodes which are operated by light. So light falls on this photodiode, and then you can be able to conduct. So some explanation there about the photodiode. An electron current flow in response to irradiation. So they can be radiated by the visible light, UV light, or infrared. So when that one happens, then the resistance inside the photodiode will be able to reduce, and it can be able to go into a conduction mode. And as far as it conducts, maybe they can use like in the burglar alarm systems, whereby when now this light is shown on the diode, then the resistance in there can be able to reduce significantly to be able to allow current to be able to flow. So Then also very important, we have what you call the photovoltaic cells. Now these are cells, they are able to convert UV light, or they can be able to convert the visible light or just generally light into electrical energy. And I'll just also want to mention about the photovoltaic cells. They convert light energy to electrical energy. They consist of a PN type of semiconductor material, usually silicon or selenium. Now this is, you can be able to see this, the circuit diagram of a photovoltaic cell. So this one here, you want to understand basically how does it able to convert light into electrical energy. So the bottom surface of the cell, which is usually away from the light, is covered with a continuous conductive contact in which a wire is attached. Then the upper part has the maximum area exposed to light, usually the P. Let's look at this diagram. You can be able to see the P type is placed on the top side, and then the N type on the bottom side. So we have the P type and the N type. When light comes in, remember the P type basically consists of holes. So the light can be able to now, this light can be able to be captured by the holes, and then in this PN junction, this is where now recombination is able to take place, and actually electrons are generated. So once these photons are able to strike this P type, it is trapped by the P type, then recombination takes place, and then now this time round, instead of light being produced, electrons are going to be able to flow, and it can be able to be stored out there. Look at the working, just as you wind up on this. When the PN junction is illuminated, electron hole pairs are generated. An electric field is established near the junction. So basically what happens here is an electric field is generated as the holes and the electrons are recombining. An electric field is going to be created near the junction by the positive and the negative ions, which are created. Remember, every time recombination takes place, we have some positive and negative ions which now move, and they're able to create an electric field, which leads to the development of a potential across the junction. So many of the electrons are pulled across the junction by the force of the electric field, and those that cross the junction contribute to the current in the cell and through the external load. So the terminal voltage is directly proportional to the intensity of the incident light. So the more the light which comes in, the more the potential is going to be developed across the PN junction. And that one is usually created by the ions. Remember, at the P type, we have the negative ions. At the N type, we have the positive. You have the positive ion. So as the recombination is taking place, then an electric field is going to be created, which can be able to pull these electrons to be able to flow here, and some of it can go to the external circuit. You can be able to see we have the external circuit can be connected through the P and the N, and the current can be able to flow through the external circuit. So these cells have actually have a wide range of applications, and one of the areas of research is going on is in what you call now the solar cells. So the solar cells can be able to function like that, and they can also be able to be used as a fuel cell, whereby now this energy which comes in can photovoltaically be able to split, for example, water, and be able to produce what you call hydrogen, which is a fuel kind of energy. So I've tried to explain the working for that. This is the bit which I was able to prepare for now. So I'm just going to open the floor maybe for the kind of special doubts we have discussed. We can be able to ask some questions and have some kind of interaction. So basically, welcome.